So after this very quick introduction to information theory and the concept of channel capacity, we are now looking at the few channel models that we have encountered in the first chapter. And then we're going to calculate and derive the capacity of those channel models. So we start with the binary symmetric channel. We recall the binary symmetric channel is a channel that has inputs x equals 0 or x equals 1, and it has outputs y equals 0, y equals 1. And with probability delta, we make an error. And with probability 1 minus delta, we transmit a bit. So we have a channel transition matrix P that looks as follows. So we have 1 minus delta, 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 1 minus delta. And this is a symmetric channel. The rows and the columns are both permutations of each other. So we can just apply our equation for symmetric channels and we can calculate the capacity. So we have W equals 2, and then the capacity is log 2 of W minus the entropy of a single column. Single column consists of the two entries, 1 minus delta and delta. And we can plug in the numbers, and this is the expression that we get. 1 plus 1 minus delta times log 2, 1 minus delta, plus delta times log 2 of delta. And this is something we define as 1 minus h of delta, where h of delta is the so-called binary entropy function. Binary entropy function is very often used. That's why we give it a special letter. It's lowercase h of delta. And it's defined as minus delta times log 2 of delta minus 1 minus delta log 2 of 1 minus delta. The capacity of the binary symmetric channel is just 1 minus the binary entropy function of delta. So here is the binary symmetric channel together with the capacity. Capacity is 1 if delta is equal to 0. We don't make an error. We can transmit 1 bit. We don't need coding even. And then the capacity quickly decreases when delta increases, up to the point when delta is equal to 1/2. For delta equals 1/2, the mutual information between input and output is 0. So there is 0 information. The output is completely independent of the input. We cannot infer anything on the input from the output. And that means the capacity is equal to 0. And then when delta increases further, the capacity grows to 1 again. So if delta is equal to 1, it means we just flip the output of the channel. And then, of course, when we just flip, we can just undo the flipping, and then we get the input again. So we have a capacity of 1 because we just do a deterministic operation. So that's the capacity of the binary symmetric channel. Next is the binary erasure channel. We saw the binary erasure channel is a very useful model for packet losses, for high signal-to-noise ratio scenarios, etc. So we have 3 output symbols. We have a third output symbol, question mark, which denotes an erasure. And the channel transition matrix looks like this. With probability 1 minus epsilon, we receive the bit correctly. So the 0 is received as a 0 with probability 1 minus epsilon. With probability epsilon, we have an erasure. And with probability 0, we make an error. There's no error on the binary erasure channel. No. Similar for 1, probability 1 minus epsilon, we receive 1. Probability epsilon, we have an erasure. So the two columns, they are permutations of each other, but the row sums are not equal. So we have no symmetricity. But we can calculate the capacity of the binary erasure channel, and we obtain the capacity if x is uniformly distributed. So if the probability that x is 0 is equal to 1/2 and is equal to the probability that x is equal to 1. And the capacity is a very simple expression. It is 1 minus epsilon. If you'd like to know how to derive this, we have an exercise in the tutorial where we're going to calculate the capacity of the binary erasure channel. So let's look at the chart. We have the binary erasure channel and its capacity here, and we see it's just a straight line. And if the erasure probability is 0, of course we have a capacity of 1. And if the erasure probability approaches 1, we will just receive question marks in this case. So there is no useful information that we can transmit over this channel, and the capacity converges to 0. And the input should be uniformly distributed. So that's the binary erasure channel. But we have a Z channel. Remember, the Z channel, a bit x equals 0 is always transmitted correctly. And a bit x equals 1 is transmitted to bit 0 with probability q. And with probability 1 minus q, it is received correctly. Because this looks like a Z, it's called a Z channel. And we saw in the first chapter it's used to model free space optical transmission, but also flash memory devices. We have a channel transition matrix that can be written as follows, and very clearly it's neither symmetric nor weakly symmetric. And you could already think of, if you want to maximize the data rate over this channel, it can make more sense to transmit zeros, because zeros are never distorted. So it's more, it's advantageous to transmit zeros, because if you transmit a 1, there is potentially an error. But you cannot only transmit zeros. If you only transmit zeros, there is no information. If you only transmit zeros, you know exactly what was transmitted, but there is no information. So there is a trade-off between the amount of information that you can transmit and the probability that you make an error. And therefore, we need to optimize the input distribution, and we essentially can do this. So we define the input distribution to be U prime is the probability that we'd like to transmit a 1. We say that probability that we transmit a 1 is U prime, probability that we transmit a 0 is 1 minus U prime. When we do random coding and we construct our random code, then this is the probability that we should choose a 1 in our codebook. And this is the probability that we should choose a 0 in our code. So this is what U prime tells us. And then we can do some calculations, and we'll not do it here. It's in the lecture notes and in the script. And also, I believe there is an exercise in the tutorial. And it's a very good exercise if you try to do it yourself. It's not that hard, it's just a little bit tedious. The expressions tend to get a little bit long, but it's not that hard. We can calculate the capacity to be equal to the binary entropy function of U prime times 1 minus Q minus U prime times the binary entropy function of Q. That's the capacity. And the optimum U prime is given by this expression. So this expression only depends on Q. That's 1 minus Q plus 1 minus Q times 2 to the power binary entropy function of Q divided by 1 minus Q. And then you take this whole expression to power minus 1. So take the inverse of this expression. That gives us the optimum U prime. Okay, so let's take a look at how this looks like. Rather unspectacular. So again, it's a curve that decreases, which makes sense. If Q is equal to 0, we have capacity of 1. And if Q approaches 1, we'll only receive zeros. There is no useful information that we can transmit. So therefore, it will decrease like this. Okay. And here is the optimum input distribution. And I'm very sorry, but my PDF display program has some issues in displaying the numbers correctly here. 0.6, 0.8, 1.0. And the color values here describe the probability. If Q is equal to 0, then P of x equals 0 is equal to P of x equals 1. Makes sense. If there is no errors, then we should just transmit 0 and 1 as with the same rate, because that gives us the maximum entropy, the maximum amount of data, essentially. And if Q gets larger, we see that we need to take a compromise, and we will need the 0 is transmitted more often than the 1, which is what we thought would be the logical case. So it's logical that you transmit more often a 0 because you don't make an error. And that's exactly what you should take home. So Q goes to 1, becomes more favorable to transmit zeros. So, and there is a compromise. It will not go exactly to transmitting only zeros, because that means that there is no information that we actually transmit. So here we plot the capacity. The blue curve is the capacity. That's the highest rate that we can achieve over the channel. But sometimes now it can become a little bit tedious to construct a code with for a very specific U, because we have different probabilities and we need to construct a new code book for every Q. So what happens if we construct a random code? Where we just use the probability that xij is equal to 0 is equal to 1/2. And we use this code for every possible value of Q. How much do we lose in data rate? This is what we show here. So this is the random code with optimal distribution of x. And the green curve is the case where we construct a random code where x is equal to 0 with probability 1/2. And we see there is a small difference, but the difference is really negligible. There is a very, very small difference, and we don't lose too much of data rate if we use a very simple random code with uniform inputs. So this is something that you should keep in mind. If you have a Z channel, it is very good if you can optimize the capacity and the input distribution of your code, but you will not lose too much if you use uniform inputs. And later, we will encounter a class of codes that are called linear codes. And in linear codes, we can only achieve this. In linear codes, we always have the probability that x equals 0 is equal to 1/2, unless we take some very specific measures that go beyond the concept of this lecture. It's called constellation shaping. And with those linear codes that are very practical, we essentially don't lose too much of data rate in this case. So that's very good to know. Great. So then let's take a look at our friend, the AWGN channel. First, we look at the very classical case, the AWGN channel, where we have no constraints on the input. So x is the case where x is a real number. This is the best possible AWGN channel that has the highest capacity. If we don't put any constraints on the input, we can play around with the input and we can select the input as we like it, with no constraints, and we get the best possible capacity. That's why it's interesting to look at this channel, although it's not practical, because our codes will give us bits. And this AWGN channel has a very well-known capacity equation, and that's shown here. Capacity of the AWGN channel is 1/2 times log 2 of 1 plus 2 times ES over N0. Or if we normalize our input to unit energy, so if ES is equal to 1, it's 1/2 times log 2 of 1 plus 1 over sigma n squared. 1/2 is due to the fact that we assume a real valued channel input. So we lose 1 degree of freedom essentially. So how should the input look like? That is also very interesting. The input should be normal distributed. So it should be normal distributed with mean 0 and variance 1. That's the best possible input for a channel. Then you get the highest capacity. It's not very easy to generate such an input, but that's the best possible we can have. So this is the upper bound. So this is how this looks like. First, we plot the capacity as a function of ES over N0, and then we plot the capacity as a function of EB over N0. Now there is a gap between those two curves. So where does this gap come from? So this gap is because we need to modify this to EB over N0. So how do we get from this one curve to the next one? Well, we start by looking at the different capacities or by looking at the different E values of ES over N0. So for instance, we pick the value ES over N0 of minus 3.01 dB. That's the value ES over N0 of 1/2. So we can go back to the previous slide and we insert here 1/2. So we insert 2 times ES over N0. So we can write this if ES over N0 is equal to 1/2. It's equal to minus 3.01 dB. That means that the capacity C is equal to 1/2 times log 2 of 1 plus 2 times 1/2 is equal to 1/2 times log 2 of 2. Log 2 of 2 is equal to 1, so this is equal to 1/2 or 0.5. Okay, so we are at 0.5. So now how do we get to EB over N0? So what we do is we start from the fact that EB over N0 or ES over N0 is equal to the rate times EB over N0. Remember chapter 1. So we can say that EB over N0 is equal to 1 over the rate times ES over N0. And now we calculate in decibel. So EB over N0 in decibel is equal to ES over N0 in decibel minus 10 times log 10 of the rate. Now, what is the rate? So if we operate at a certain ES of n0, then we assume that the rate is equal to the capacity because we choose the best possible code that we can have. The best possible code has a rate equal to the capacity. So we insert here, we insert the capacity because the rate is equal to C. So we can do this for our example. We can do then say EB over N0 in dB is minus 3.01 dB minus 10 times log 10 of 0.5. And this is equal to 0 dB. So at a capacity of 0.5, we are at 0 dB. And now we repeat this for every other point. And for every point pair of point ES over N0 and C, we get a point EB over N0 and C. So that's how we can find this curve of the capacity as a function of the energy per bit divided by N0. Okay, now we see this curve kind of converges to some value, and we can essentially also calculate this value, and that is the absolute communication limit. So that's the worst channel we can communicate over. And in order to calculate this, we start from the capacity expression. So we have our AWGN capacity, 1/2 times log 2 of 1 plus 2 times the rate times EB over N0. So if we had capacity, we can communicate at most with the rate. So the rate is smaller or equal than the capacity. So we have a rate that is smaller or equal than the capacity. And here we have a rate as well. So now we solve this expression for EB over N0. And just rearranging this a little bit, try for yourself if you can do this rearrangement, gives us 1 over, EB over N0 should be larger or equal than 1 over 2R times 2 to the power 2R minus 1. So now we let the rate go to 0. Now we assume we have a very bad channel and the rate goes to 0. So what is the EB over N0 in that case? So we calculate the limit when the rate goes to 0 of EB over N0. Then this is 2 times 2 to the power 2R minus 1 divided by 2R. A very bad limit because it is 0 divided by 0. Then we can use our good old friend L'Hopital's rule by taking the derivative of the numerator and the denominator. We get another expression, equivalent expression for the limit. So the derivative of the denominator is simple, that's 2. The derivative of the numerator, that's 2 to the power 2R plus 1 times natural logarithm of 2, because we can rewrite 2 to the power 2R is equal to e to the power 2R times ln of 2. And then just taking the derivative and multiplying with the inner derivative. That gives us 2 to the power 2R plus 1 times log 2. And now we can essentially calculate the limit when R goes to 0. This guy, when R goes to 0, this guy goes to 1. So this is a 2, 2 and 2 cancels. So we end up with natural logarithm of 2. This is minus 1.59 dB. And this is essentially where we are. Here this is minus 1.59 decibel. The absolute communication limit. All right. So we have the AWGN channel, we have the absolute communication limit. Now we're looking at the practical channel, which is the binary input AWGN channel. Binary input AWGN channel, now we have the constraint that the input X is plus or minus 1. So what is the capacity? Well, that's a little bit bad because we don't have a nice expression for the capacity. We can only calculate the capacity numerically. It's a little bit unfortunate. So here is the expression for the capacity. 1/2 times the sum over x equal to plus or minus 1 times the integral of f of y given x times log 2 of f of y given x divided by f of y. We can simplify this a little bit to be equal to minus the integral of f of y times log 2 f of y dy minus 1/2 times log 2 of 2 pi e Euler's e times sigma n squared. And f of y given x is the usual Gaussian distribution, and f of y is just 1/2 times f of y given x plus f of y given x equals minus 1. And the capacity is achieved if p of x equals plus 1 is equal to p of x equals minus 1 is equal to 1/2. And again, in the tutorial, we have a section on an exercise where we derive this capacity step by step. So a little bit unfortunate, we can not have a simple expression that we can solve with pen and paper, but with the computer we can plot this. That's what we can do, and this is what we get. So also we have, let's first take a look at this. So we see that for small signal to noise ratio, bad channel conditions, we have a lot of noise, the capacity of the binary input AWGN almost looks like the capacity of the AWGN channel. And then there is a deviation because this one will saturate to 1, which makes sense. If we have a binary input, there is at most 1 bit that we can put into a plus or minus 1. We cannot put 2 bits into plus or minus 1. Just put 1 bit into a plus or minus 1. And if we can then do the same exercise as before and plot the curves as a function of EB over N0. We do this by numerical integration. And here we also have a Jupyter notebook that is called binary input AWGN capacity. So let's take a short look at this Jupyter notebook. And I will just need to start everything and get everything up and ready. So here we go. So here we go, and we can call binary input AWGN capacity. So let's increase the font size a little bit, and I hope that still works. That looks amazing. So again, we define the different functions. We define f of y given x, just the Gaussian, the usual Gaussian distribution. Then we define f of y, and then we have an integrand, which we indicate, which is f of y times log 2 f of y. And then the capacity is given by this expression. And we just numerically integrate using the integrate function from numpy. And that's it. There is an alternative way for those of you who are interested. If you want to numerically calculate those integrals, you can use something called the Gauss-Hermite quadrature. Essentially, what it does is if we have an integral of this form, e to the power minus x squared times f of x dx, you can approximate this integral by a finite sum over wi times f of xi, where wi and xi are weights and roots of the so-called Hermite polynomials. And then using the Gauss-Hermite quadrature, we can rewrite the integral that we had here in the following form. So that's just a rewritten version of this integral. We need to do a little bit of substitution to get it exactly in this form. And that's also something we can do. This Gauss-Hermite polynomials, they are integrated into NumPy. So we can just call the weights and the roots. We use a sum with 40 summons that is sufficient for enough precision. And then we can essentially do the plotting. So we can do the plotting, and here we also describe how we do this change. So EB over N0 in dB is going to be ES over N0 in dB minus 10 times log 10 of the capacity. And then essentially we can reproduce the plots that we saw in the lecture. It's calculating a little bit, it's formatting. Plotting in NumPy is a little bit slow, but you get this very nice plots exactly as we expected. Okay, so we have solved the binary input AWGN case. Now the next channel that we're looking at is the hard decision binary input AWGN channel. So now the difference is that we put a decision at the end of the channel, at the output of the channel. And this decision, we have seen, transforms this hard decision binary input AWGN channel into a binary symmetric channel. So we have a binary symmetric channel with an error probability delta, which is equal to Q of 1 over sigma n, or 1/2 times the complementary error function of square root of ES over N0. And using the Q function or the complementary error function and delta, we can now calculate the capacity, because we know that the capacity C is equal to 1 minus the binary entropy function of delta. So it's 1 minus the binary entropy function of Q of 1 over sigma n. That's the capacity. Or 1 minus binary entropy function of the Q function of square root of 2 times ES over N0. Okay, so with this expression, we can plug this expression in and generate a plot. And this is what we do here. On the right-hand side, just for simplicity, I left away the blue curve. We can also plot it, and that's how it looks like. So we see that there is a considerable gap in terms of capacity. So we see that we have a vertical gap, which means that the rate of our codes must be smaller. If we have a channel with a certain signal-to-noise ratio, the gap is there, so the rate must be significantly smaller. But we also have a horizontal gap. This horizontal gap means that if we make a hard decision at the channel output, we need a signal-to-noise ratio that is by 2 dB, roughly, 1.5 to 2 dB larger compared to the case when we don't do this decision. So we need 2 dB or 1.5 dB higher signal-to-noise ratio when we make this hard decision. And that's something we should take care of, because we essentially, by doing this decision, we destroy information. I told you in one of the previous videos, we have good noise and bad noise. So the good noise, which is essentially a value that has been received almost surely correctly, this information is completely destroyed by the decision. And that's why we have this gap here. again, we can take a look at how to compute this, and we can go a little bit further. Just a moment. And here we have just computing the capacity of the binary input AWGN channel with the decision. So essentially, we just calculate delta. So 1 over sigma n, and then apply the Q function. The Q function in Python is called norm.sf. It's called survival function. That's a different name for the Q function. So we need to look at the literature or the documentation of your software a little bit to find the Q function. In Python, it's called survivor function. In MATLAB, it's called qfunc. And then we can just plot everything. And here you can see the two plots that are also in the lecture. Great. So now we have the capacity of the hard decision binary input AWGN channel and the binary input AWGN channel. So take home message, if you can avoid this decision, you should avoid it, because here we lose 1.5 to 2 dB in signal to noise ratio, as you can see. The loss will be less severe if the rate of the code is large, but especially for low rates, the loss will be quite severe. So when we compare coding schemes, we use these so-called spectral efficiency charts that we have just seen, and we can compare coding schemes. So here I took this example code of rate 4/7. The rate is equal to 4/7 of this code, and we plot the waterfall curve. So we know how the bit error rate evolves as a function of the ES over N0 or as a function of EB over N0. And we saw that here the gain, the net coding gain, is smaller than the coding gain. So recall, the net coding gain is when we look at EB over N0, where we need to spend energy to transmit the extra parity bits, so we can transmit less energy per information bit. And ES over N0 has a bigger gap. That's the gross coding gain. So now what we do is we define the performance in the spectral efficiency chart. So here the simulation was over binary input AWGN channel. And what we do is now we take a look at the code. So, and we define a target bit error rate, and assume the target bit error rate is 10 to the power minus 8. And then we look at where this code performs at 10 to the power minus 8. And it performs here roughly at, say it's, I would need to guess, but this is approximately 8.8 dB. And in terms of EB over N0, it performs roughly at 10.4 dB. So now we take these into the spectral efficiency chart. So we have a rate of 4/7. So what is 4/7 numerically? We divide 4 by 7. This is approximately equal to 0.6, equal to 0.57. And we saw that we need ES over N0 of 8.8 dB to achieve a bit error rate of 10 to the power minus 8. So this is the point that we would insert somewhere outside of this region. And also here, we cannot insert the point. So we would have a point that we will insert somewhere here, and then we will show it in the spectral efficiency chart. So we can For instance, think of a code that works better, and we're going to see better codes. So for instance, if we have a code that has a performance like this, and it has a performance in EB of n0 like, sorry, I need to kind of guess where we are. So this is 4. I need to come backwards a little bit. So it should look like this. So this is a code where we are at 4 dB, yes of n0, and here we are at 5.8 dB roughly. So this is a code that we can insert on the spectral efficiency chart. So we had 4 dB, that's the operating point. So we are at a rate or capacity of 0.6, and we need 4 dB ES of n0, or 5.8 dB EB of n0. So that's the operating point at a bit error rate of 10 to the power minus 8. So you define a bit error rate, target bit error rate, you have the code, you look at the performance of the code, and then you insert this performance in this spectral efficiency chart. And we have an operating point here, and we can see that there is a pretty big gap between the capacity and this operating point, both in terms of EB of n0, but also in terms of rate or capacity. So what does this mean? It means that if we fix the rate of the code, we fix R equals 4/7, it means that with a better code, we could operate at a signal to noise ratio that is 5 dB lower, more than 5 dB. This is a 5 dB gap. That's what it means. So if we fix this rate with a better code, we can operate at a lower signal to noise ratio. That's the horizontal gap. What is the vertical gap? The vertical gap means that if we have this signal to noise ratio of our channel, this EB over n0, then we could increase the rate of the code and transmit more information. Same here, if we have a fixed signal to noise ratio of the channel, we can increase the rate of the code and transmit more net information and less parity bits. So that's what a better code can deliver us. Either we can increase the throughput or the data rate for a fixed signal to noise ratio, or we can operate at a lower signal to noise ratio. So now we have looked at the capacity of different coding schemes and of different channels. And we have the spectral efficiency chart, which is a measure that we're going to use of comparing different coding schemes in the future. So with this, we have also reached the end of this video. And in the next video, we will look at a special approach on information theory, but information theory at finite lengths. So far, we have seen that information theory and capacity assumes that the length of the code n goes to infinity. Now in practice, this is usually not the case. We deal with finite length codes. So what we need to do in practice is we need to have a finite length. Now what is the capacity of a channel if our code only has a finite length n? This is what we're going to solve in the next video. Thank you for watching.